welcome to Analog Output. It's been a while due to, good old procrastination and other reasons. One reason being time taken to try to deal with some problems with this thing, which is one of my newer modules. And this is a voltage controlled low frequency oscillator. It's based on a circuit board from Music from Outer Space, designed by Ray Wilson, and put it behind a Cosmo format front panel. This thing's built pretty much as Wilson designed, with a couple of exceptions. One thing is there's this auxiliary circuit board here, which I'm going to talk about in another video. It's interesting, but it doesn't affect what I'm going to be talking about today. The other thing which does affect a little bit what I'm talking about is I added a couple of attenuators on the front panel, one for the frequency control voltage and one for the pulse width modulation control voltage. So these are just a couple of potentiometers mounted on the front panel to attenuate those signals. And that affects what I'm talking about today, but I just want to emphasize that if these attenuators were not here, you'd probably want to attenuate the incoming control voltages anyway a lot of the time, so you'd probably run them through an external attenuator module. So whether the attenuator is here or over here somewhere in the next module over doesn't really matter. It would behave the same way as far as that's concerned. So what's going on? Let me show you what I noticed when I built this thing and plugged it in and started looking at it. Okay, here we have the module set up. We're looking at the square wave or pulse wave output. We've got the pulse width set to minimum. Pay no attention to where the lines are on the knobs. I just kind of stuck them on at random. But pulse width is at minimum. Pulse width modulation level is set at minimum as well. Now, if we look at the pulse width here, as I turn the knob, you can see it doesn't change very much. It changes a little bit, from less than 50% to greater than 50%, but not very much. Okay, now if I set the pulse width to minimum, and if I turn up the pulse width modulation level, this is with nothing plugged into the pulse width modulation. There's no control voltage here. I'm just turning a knob that's connected to an empty jack. And when I turn that, you can see the pulse width gets a lot narrower. I've got it up to maximum. Pulse width has gone down quite a lot. And now if I manipulate the pulse width knob, it gets to a much larger width. So the range of pulse width depends upon the setting of the pulse width modulation level knob, even with no pulse width modulation control voltage plugged in. Okay, what's going on? Well, this is kind of a simplified version of what's going on in the pulse width modulation section of the schematic. You've got a voltage coming in. This is supposed to determine the pulse width. It goes into an op-amp configured as a comparator, which uses the ramp wave to make the pulse wave, and the voltage coming into the comparator from here determines what the pulse width is going to be. And you also have the control voltage input, which also connects to the same point through a couple of resistors. Now, if there's no control voltage plugged in, then this point is floating. It's not connected to any particular voltage, and what that means is the voltage at this point is equal to the voltage at this point, the voltage coming in from the pulse width control. However, if you plug in a control voltage, now you have a connection to a particular voltage, and so you have a voltage divider formed by these two resistors with this voltage at the top and the control voltage at the bottom. And in particular, if you have a 0-volt control voltage, then the voltage at this point now becomes half of the voltage at this point. So depending on whether you have no control voltage plugged in or a 0-volt control voltage plugged in, it will change the pulse width and it will change the pulse width range by a factor of 2. It'll make the pulse width range a factor of 2 narrower if you have a 0-volt control voltage plugged in. And I consider that to be undesirable behavior. I would like it to not change the pulse width range if I plug a 0-volt control voltage in. Now, one way to address that is if you used a switched jack for the control voltage input and you connected the tip switch to ground. And what that means is when you have nothing plugged in, then by default it'll connect to ground. And when you plug in a control voltage, it'll connect to the control voltage. And so if you plug in a 0 control voltage, it will do the same thing as if you have no control voltage plugged in at all. So that will stop it from changing its behavior when you plug a control voltage in. Unfortunately, what it means is you then have permanently the behavior where the pulse width range is half what it would have been if you had left that input floating. Now, another thing you could do is you could do what I did, which is install an attenuator on the front panel. And then this point is always connected to ground through the control voltage attenuator. So there's always a voltage divider here, and the behavior of this voltage divider is going to depend on the setting of the control voltage potentiometer. You got 10k ohms in this resistor here. This resistor is 10k, and I used 100k for this potentiometer. So depending on where the potentiometer is sitting, the bottom of this voltage divider can be anywhere from 10k to 110k, and the top is 10k. So the voltage that you get here is going to be dependent on what setting you use for the control voltage attenuator, because that's going to change the voltage divider, regardless of whether there's actually a control voltage plugged in or not. That doesn't matter. The different settings of the potentiometer will change this voltage divider, and so it will change the relationship between this voltage and that voltage. And so you'll get changes in the pulse width when you change the control voltage potentiometer, even with no control voltage plugged in. That I consider undesirable behavior. However, there's more to this story than this, because, yeah, you do have this voltage divider which makes this voltage be different from that voltage. However, there's also the fact that you have another voltage divider, which is the pulse width potentiometer here, and the two fixed resistors associated with that. So you've got 12 volts here, you've got a fixed 100k resistor, you've got a 100k potentiometer, you got another 100k resistor, you've got minus 12 volts here. And if this weren't connected to anything, then when you change the potentiometer, you would get something in the range from minus 4 volts to plus 4 volts. But this is connected to a 10k resistor, which then connects to another 10k resistor, which, if you have a control voltage plugged in or if you have an attenuator connected, then that connects possibly through an additional resistance to ground. If the attenuator is set to its minimum, then what you have is 20k from here to ground on this path and 100k on this path, and so most of the current that enters the top of the voltage divider is going to go out through the wiper and not down to the bottom, and that's going to distort the behavior of the voltage divider. Normally with a voltage divider you want to have negligible current at the output, and here you have most of the current coming out at the output. What that means is that the voltage here is reduced from what it would be if there were no connection to ground via this path. And then, of course, your other voltage divider means that this voltage is reduced with respect to that voltage, and so instead of getting minus 4 volts to 4 volts here, and then minus 4 volts to 4 volts here, what you end up with is actually something like minus half a volt to plus half a volt. It's greatly, greatly reduced from what it should be. And if you change the control voltage attenuator, that changes the resistance in this path, that changes the current through this path, that changes the behavior of the pulse width adjustment knob. So the control voltage attenuator interferes with the pulse width adjustment. And this works symmetrically. The pulse width adjustment interferes with the control voltage attenuator. If you have a control voltage coming in and you've attenuated it a certain amount, if you change the pulse width control, it's going to change the amount that the control voltage is attenuated. These two controls are interfering with each other. And the reason they're interfering with each other is because these two mixing resistors are too small. They're 10K compared to 100K for these potentiometers. These two attenuators are voltage dividers. With a voltage divider, normally you want a large resistance to ground at the output. Here you have potentially a small resistance to ground. Now, it's a little puzzling to me why it was designed this way. If this were designed by some random bozo on the internet, I would say, well, he just doesn't understand how voltage dividers work. But this was designed by Ray Wilson, who I think knew very well how voltage dividers work, and I'm very surprised that he designed it this way. Maybe he had some four-dimensional chess reason for designing it this way, but I can't see what that reason would be, and it definitely leads to some behavior that I don't like. So, what to do about it? Well, one thing I did was I took a look at a couple of other oscillator designs. One of them was the voltage-controlled oscillator by USynth, and he's got a very similar setup there with the pulse width control and the pulse width control voltage attenuator built into it, and they're both going into a comparator. Very similar thing, except that he's got different values for these resistances. He's got smaller values for the attenuator potentiometers, and he's got larger values for the input resistors. And I don't have this USynth VCO, but it's easy enough to do a little simulation of this part of it, and using the values that he used, you get much different behavior. You get negligible amounts of interference between one control and the other one. So I decided what I wanted to do was change the values of these potentiometers and these resistors to be something more like the ones that were used by Evosong. So I changed the potentiometers from 100K to 25K, and I changed these summing resistors from 10K to 200K. So these things I made them 20 times larger. I made the attenuators 4 times smaller. And now, instead of the potentiometers being much larger than the summing resistors, now the summing resistors are larger than the potentiometers. And that should address the problem of one control interfering with the other control. Now, initially I thought also the fixed resistors ought to be similarly reduced from 100K to about 25K, or actually 22K is what I used. But that doesn't address the other problem. The other problem being that you have this voltage divider here, and so you have about half the voltage here that you have here. So in order to get something like minus 4 volts to 4 volts here, you actually need something more like minus 8 volts to 8 volts here. And to get that, I had to change these two fixed resistors from 100K all the way down to 3.3K. And that gives a voltage range of about plus and minus 4 volts going into the comparator. So now let's look at how it behaves. All right, then, here we have a pulse wave with about 50% duty cycle. And if we change the pulse width knob, we can get that down right to a little less than 10%. And if we turn it the other way, we can get that pulse width up to pretty close to 90%. So we've got a good, nice range on the pulse width, and then if we change the pulse width control voltage all the way from one end to the other, there's just no visible change in the pulse width or the pulse width range. We still go around 90% to around a little less than 10%. So we fixed it. Now, I mentioned I looked at a couple of other oscillators. One was the USynth voltage controlled oscillator. The other was the Music from Outer Space voltage controlled oscillator, which I had just built. I said to myself, well, how did he handle the pulse width controls for that? And I dragged out the schematics and looked at it, and lo and behold, it's nearly identical. I mean, there's some differences, but there's still the 100K potentiometer for the pulse width control. There's still the 10K mixing resistors. There's still the control voltage, which in his version is floating. And if you do what I did and you build in a control voltage attenuator, then that makes a voltage divider at the comparator input. And so the comparator input voltage is smaller than the voltage that you get out of the pulse width control and all of that. So it ought to have the same problem. And I plugged it in and looked at it, and it had the same problem. Now, at this point, I should mention, yeah, I did breadboard the low frequency oscillator. I did breadboard the voltage controlled oscillator. I did build the VCO, and then I built the low frequency oscillator. And it wasn't until that point that I discovered this problem. So a little embarrassing there. I had like 3 opportunities before this to spot this problem, and I didn't. Well, anyway, finally did. Anyway, voltage controlled oscillator, same problem. Same solution. I changed the potentiometers from 100K to 25K. I changed the summing resistors from 10K to 200K. And in the VCO, as you might remember from an earlier video, instead of having 12 volts connected through fixed resistors on the pulse width control, there's a fancy thing where he uses a track and hold kind of circuit to set those voltages according to the maximum and minimum of the ramp wave voltages. And what I found was that gave too small a pulse width range. Well, the reason it gives too small a pulse width range is because of this voltage divider thing. If I didn't have the attenuator connected, it would have given me a larger pulse width range. And the way I fixed that was I put in a little op amp there to amplify those 2 voltages, but I was only amplifying them by about 1.33. And with these modifications in place, the effect of the voltage divider at the comparator input is to reduce the voltages off of this by a factor of 2. And so I think what that means is that this amplifier ought to amplify by a factor of 2. So I rebuilt this amplifier to give me a factor of 2 amplification. And now I've got nice, stable, non-interference between the pulse width and pulse width modulation controls. And I've got a nice big range on the pulse widths for the VCO as well. So that's the saga after a lot of messing around and trying to understand things and substituting parts. I've got both of these things working with pulse widths, pulse width ranges, pulse width control voltages working the way I think that they should. I'm going to be back again soon with another video talking about that thing there, which relates to that switch there and that input there. Those were not there in Ray Wilson's design. I've added that as a new feature. So stay tuned, and you'll see that video coming up soon, and hopefully some more interesting stuff coming soon after that. See you next time on Analog Output.